go. Okay, good. So, yeah, welcome back. So today we are at point 3. And as I mentioned last time, today I want to really make an important step because so far we discussed how to really simulate quantum dynamics just on the full Hilbert space with the full state vector. And we were thinking about how to push performance there using the concept of sparse matrices and Krylov space. And we used this to simulate the spin model dynamics of quite large systems, so up to more than 20 of those spins, and saw some interesting physics. Today, now I want to really make the step and go ahead, and instead of using this full Hilbert space, use an approximate, actually an extreme approximation of the wave function. So kind of what I want today, I want to introduce really mean field simulations for these spin models by making, as you already heard before, mean field meaning you make a product state ansatz. So today this is a quite rough approximation that we're going to look at. And then tomorrow I want to talk a little bit about how to go beyond that rough approximation to go something which is called matrix product state, which is sort of an extended state approximation, much better than the product state. All right, so just to recap, again, the last time we now looked at this Krylov space ideas. This was really a way to use the fact that a matrix is sparse. And the idea is that one solves really the problem, the quantum problem, be it a ground state diagonalization or be it a matrix exponential, on a much smaller state space, which one construct from these Krylov vectors after a Gram-Schmidt procedure. And this was what we did mostly. And then we showed how to use this to really simulate dynamics in these long-range spin models. And then on the PDFs, I had a lot of stuff about open systems that I skipped because we didn't have time. But I think it's very nicely written down. So if you're interested in this, I think these PDF slides that you will get are going to be a good resource. OK, so the plan for today, as I just mentioned. So here I kind of sketch it as a rough picture. So imagine this is your whole Hilbert space. And so far, we really use the whole Hilbert space. So our state vector that we defined so far really makes use of all of the 2 to the n basis states for n spins in this system. Today, I set to a very rough approximation, and I say I will only consider states which are product states between all the spins. So this is spin 1, spin 2, and spin n, and so on. And then, of course, states that I can write like this, right? There are much less states. You already see you have 2 complex amplitudes for each of the state. So you have only 2 times n complex numbers to describe this. Much less than 2 to the power of n. So this is really a very tiny corner of the Hilbert space. But we will see how to write down equations of motions for that tiny corner of the Hilbert space. So the first part today is I want to just show you how to derive the equations of motions for that tiny corner of the Hilbert space. And then we will see, as always, as you've seen, for example, also in the BEC lectures, if you do mean field approximations, you end up with nonlinear equations, like, for example, the Gross-Peters key equation. The same happens for the spin models. Whenever you make this sort of semi-classical approximation, equations become nonlinear, and then we cannot use these diagonalization ideas anymore. So then what I want to introduce in the second part, I want to introduce these so-called Runge-Kutta methods, which is just a general like Swiss Army knife for simulating any type of ordinary differential equation. And I will introduce these methods. They are quite simple. This is not going to take long. And then finally, I will go, again, sort of tutorial style, just to show how to implement this type of Runge-Kutta methods for our spin model dynamics. And we will analyze a bit in which approximation this mean field is a good approximation and when it's not a good approximation. And if I have time, this is again sort of the overlap here. I may shift this to the next lecture. I want to also look a bit at mean field dynamics for bosonic systems, so really look at the Gross-Peters key equations and just show you something funny that's happening there, showing some movies essentially. All right, so the first 2 parts are really just going to be derivations and theory, and then towards the end, we go hands-on again. OK, so here's essentially what I really just said. So far what we did is we all considered exact simulations, and now I want to approximate my states on a small corner of the Hilbert space. Again, the exact Hilbert space, I want to, for now, stay with these spin models. So I have, again, this n2 level system. So the exact Hilbert space is 2 to the power of n. However, what I'm going to do now, I'm going to make a rough approximation. The rough approximation is really, if I write down this many spin state here, but I can write it really as the sum over the indices, right? So this is kind of a coefficient tensor. We will see, this will come back next time again too. Right, so this is really the full state vector of my system of n spins. Here I just write it a little bit different. I can write it as one vector with one index, right, where the index runs through the whole Hilbert space. Or I can write it as an object with many indices, with n indices. And each of these indices can have the value 0 or 1. Right, so now this is kind of a high-dimensional tensor here. Each of these dimensions has a dimension 2. And my basis states are just really these computational states that we already introduced the last time. Right, it's a bit of a different way of writing the state vector as an object which has actually n indices instead of one index, which is power 2 to the n. But one can always do that. And sort of the product state approximation, this mean field corner, really means that now I take this state tensor and I just write it, instead of keeping the whole tensor, which has 2 to the n elements, I just write it something like tensor for spin 1 times vector for spin 1 times vector for spin 2, and so on. Right, so what I have now, I will have a representation where just for each of these two-level systems, I have just two complex numbers which describe the state of this local two-level system. But I neglect a lot of states in the whole Hilbert space of the big system. Right, so now I really make an approximation where my complexity is now just of order n. Right, so here they are now just really n of these vectors, so 2n complex numbers. Whereas here in this tensor, I have 2 to the n elements. So I have much less numbers to describe my state. So obviously, I will throw away a lot of information. But I can do much larger systems because I can store much bigger system sizes. All right, so in the first part, I really want to derive now the equations of motion that I get if I make this mean field approximation. And there are several ways of doing this. I will actually compare a bit two of them. But the one that I think is conceptually easiest is the following. So what I want to do is I want to again use kind of a Bloch vector representation of your local spin. Right? So this was already introduced. It was introduced in terms of these two angles, theta and phi. But I can also just write an x component, a y component, and a z component of my two-level system Bloch vector. So any state of a single two-level system, I can just write like this with this Bloch vector where I have this x component, y component, and z component. And x is really the expectation value of sigma x, y is expectation value of sigma y, and z is the expectation value of sigma z. So the way I want to derive now this mean field product state equations of motions is the following. I want to start from the Heisenberg equation of motion for my Pauli matrix X. And then once I get the equations for the Heisenberg evolution, I will take expectation values. And then whenever I take these expectation values in the equations of motions, what I will do is, as soon as I encounter something like a correlation function, like for example, sigma ix, sigma iy, I will just write this as a factorized product, right? Because this comes from the fact that I write my state really as a product state. Okay, and this is where the approximation happens. Okay, so here the notation may be a bit clumsy, but I wanted to do it for really a very general spin model with two-body interactions. So far we looked at this transverse easing model, but in a very most general form I can write, well, not the most general form, but the almost most general form, I can write a spin model with sort of single spin terms and with sort of two spin terms. So I want to look at the general Hamiltonian that has the following form, and I'm going to derive the equations of motions for that Hamiltonian. And then I will go back to the special case of this transverse easing model. But there's many more models included in this Hamiltonian. So you have now then a collection of the formulas to actually use. Okay, a few comments here. So here I have really the local field terms. Right? So here for each of the spins, so this term here just has a local field in an x direction, in a y direction, and in a z direction. In addition, I write the interaction term a little bit different than last time. Last time I was summing over the pairwise interactions using always an index j being larger than I, so I sum only the pairs once. Here now I want to really sum over all of the terms, and to correct for the double counting, I add a 1/2 in front. Which means then, of course, by definition, I define that diagonal terms of these things are defined as 0, so there's no self-interaction of each of the spins. And of course, they are all symmetric interactions in the sense that Vij is Vji. And I have pairwise interactions of the form XX, YY, and ZZ. Of course, there are also some models where I have things like XY plus YX and so on, but this, okay, I mean, the derivation is very general. It's quite easy to redo it for those terms too. Okay, so good. So let's start with the strategy of deriving these equations of motions, and let's start very simple in the beginning. So as I said, I have two Hamiltonian terms. The one is this H1, this is just the single qubit terms. And then I have the H2, which is the pairwise interaction terms. And this is all I have for now. So let's first look just at the H1 terms here. Okay, so let's start, for example, from the Heisenberg equation motion of the Pauli X operator. So I write something like d over dt sigma x for spin m. So I pick one spin, call it m. This is the Pauli matrix, and the Heisenberg equation of motion is I times Hamiltonian commutator with the sigma m, mx. Okay, so now I can take all of these local terms from my local Hamiltonian here, so from this term here. Right, so, and I just only have to look for the terms that do not commute with this. Okay, so it's clear, for example, that the sigma x term here in this term will commute, so this doesn't give any evolution, naturally. But the only two terms that give me an evolution is where in the Hamiltonian I have the term sigma ym and sigma zm with the corresponding fields in front. Right, you see this? None of the other terms matters. I have here the sum of all of the other spins. But if m is not the same as n, I get again a Pauli matrix that commutes, so it doesn't give rise to any evolution. Okay, so this is the Heisenberg equation of motion, so I can evaluate this commutator here. Right, I can use this normal identity here with this Levi-Civita tensor, this fully antisymmetric tensor, which tells me that if I have the commutators between a Pauli matrix alpha and a Pauli matrix beta, then it's going to give me a Pauli matrix gamma. And this only gives me something if, for example, this is x, y, and z. If it's in this order, it's +1. So if it's an even permutation. If, on the other hand, it's something like z, y, and x, then it's going to give me a -1. Okay? So this needs now for these terms here. Let's look at this one, for example. So here I have y, x, and I know it's going to give me a sigma z. Right, so then I have x, z, y, so this is really, then this factor is -1. So I get a -2i, which gives me a +2 in the end in front of this, and this term gives sigma my, sigma z. And this one has the opposite sign, because here I get an even permutation, x, y, z. So this gives me -2 sigma y. Okay, so this is how you derive this type of equations from the single spin terms. And they are quite intuitive, I would say, because the equation that you get is really an equation for the x component of your spin m. And you see that you get a precession, we had that word before, a precession of that component that comes from a field in the y direction and a field from the z direction. So you actually see that this is exactly the same as really a classical spin. So alternatively, one could also, if you don't know this formalism, don't worry, but going back to fully classical physics, taking classical spins, one really arrives at the same types of equations of motions, just using this Poisson bracket for spins. And it gives exactly the same results. So here I've just written it down. So I will skip a bit of time to have some more time for the fun stuff in the end. But it's really fundamentally the same, which really means that these terms, right, in that sense, your quantum spins evolve exactly the same way as the classical spins, with the only differences, of course, that you can have sort of then projective measurements of the spin, and then you can get some quantum effects which are not inherent to classical spins, but otherwise it's completely equivalent. Okay, and the other two equations for sigma y and sigma z give now the corresponding different terms here, so I will not derive them, but you can try it for yourself. But the bottom line is just if you have the single field terms, of course they just give a rise to a precession of your Bloch vector. Okay. Good, what's of course more interesting here, and there's a lot of formulas here, so don't be scared. It just looks pretty ugly because I wrote it down for this very general Hamiltonian, but conceptually it's actually very, very simple. So now we look at these two-body terms. Right, so again, I make the example only for the sigma x component, and then I leave the sigma y and the sigma z component of the spin m. I leave it as an exercise. So here now, looking at the Heisenberg equation with the Hamiltonian H2, we have again to just look for all of the terms that do not commute with this sigma m x term. Okay, so let's have a look at the different terms. So here I just really write things down. So I already see now, here's the Hamiltonian, right? So I need to have the term from the sum where one of the indices here, either the index I or the index j is the same as m, right? So I can get either, because I always have these two terms, I can get either a term where the index I is the same as m, this is this one here, and I get a term where the index j is the same as m. Okay, but the sum over j here and the sum over I still remains, because this is the sum for the second Pauli matrix, which is for that first term is out here. This is sigma jy, and for this term it's in the front of the commutator. Okay, and the only terms that I get, of course, is the yy, because the xx term again gives me a term where sigma x commutes with itself. So I only get the yy term and the sigma z term for both those two cases. Okay, now the same game as before. I just use again just this commutator between Pauli matrices, which are very easy to know. And then let's take just one example. Here, for example, I have again, but this is the same as before. I have again a y, x, so this is going to give me something which is minus 2i sigma z. Right, so this gives me minus 2 here. I had this factor of 2, which I cancel with this factor 1 over 2 here. And then I get an I, which gives me another minus sign out here. Okay? And the same is true for the second term, and here just use the fact that Vij is the same as Vji. And for this term here, again, I get just the thing with just the opposite sign in the end. Here I have a plus sign, here I get a minus sign for those terms. Okay, good. Then just putting these things together, also noting that j cannot be m because the diagonal terms are 0. I can write it in this relatively simple form here. And this is now where the interesting stuff is going to happen, because so far, right, this is the Heisenberg equation of motion. And what you see here is now, if you evolve this operator really in the Heisenberg picture, this is the evolution of your sigma x matrix for spin m. And you see that this evolution of the sigma m x matrix now couples to a correlation function, which is zy and yz. Okay? Which means that if I look just at the equations only of my sigma x alone, it's not going to give me a closed equation because it couples to these objects here. So I also have to write down an equation of motion for these operators here. And then if I keep this hierarchy, I will see that these two-body operators couple to terms with 3 operators and 4 operators, and I get this whole hierarchy. But there, this is the point where we do our mean field approximation, right, our factorization ansatz. And what we're going to say is we're going to make our approximation again that we look only at expectation values of x, y, and z. And here we now factorize these 2-point correlations. And then my equations become closed immediately, right? Because now I have the equation of x here, which just depends on only z and y. And for those, I can derive equations too. Right? I will not do it here. I will just show the result. But this is how this goes. This is where really this mean field approximation happens. All right, so the full result is then looking something like this. This is all of the terms that come only from the two-body correlations, for the two-body interactions in the Hamiltonian. So I have the equations of x, y, and z. And again, you see a certain symmetry here in the sense, because all of this comes from this fully antisymmetric tensor. So you see that here, for example, you have a term which is like z. If I go x, z, y, right? So this is x, y, z in reverse. So this is an odd permutation. So then all of the odd permutations have a plus sign here, and all of the even permutations are going to have a minus sign. So after a while, one can just really guess these equations of motions because they just come really from the way that you have this antisymmetric tensor. Okay, so now this is a good point to discuss why this is called mean field. Because if you stare a little bit at this equation of x now, you see if I compare it before to the trivial equation here, this was just an external field, right? I had a field in a y direction, coupling, depending on the z component, gives me something that changes the x component. Now here, again, I have something which actually is a field in the y direction, coupling to the z component, gives me a change of the x component. Right, so the way that to interpret this is actually that here this is a sum over all the other spins, which are not the same as the spin m. And all of the other spins, they create a field on my spin m. Right, so if I sum over this index j here, I have the, let's say my m is 1, then my spin 2 creates a field on my spin 1, the spin 3 creates a field on the spin 1, and so on. So in the end, this expression here is a mean field that's created, it's the average field created by all of the other y components, and this mean field gives rise to a precession of the spin that I'm just currently looking at.
This precession for A1 will still happen? I mean, the sequence for the equation that we wrote for the Heisenberg equation, it's inspired by precession.
Yes.
Precession with a difference. We're going to see.
Well, this is the thing, because now, you see, now it depends on the y components of the other spins at a certain point in time. Yes, but the y component will also change in time. So this is why I mean this is going to be nonlinear equations. Right? If you have a fixed field, then this field is just there and your spin precesses around the field. But now this field that's created from the other spins is also going to change in time. Right? So it becomes nonlinear problem.
So the frequency depends on the time also.
Yes. So that what gives rise to the interesting physics here. Okay, and that's why it's called the mean field approximation. Yes?
Is there an interpretation about how correlations in the quantum problem become nonlinearities in the semi-classical or
there's not a general framework. I am aware of some works where, for example, there's something like spin synchronization happening classically, because in this nonlinear dynamics that you get here, sometimes you get synchronization of classical spins. And there, it's known that this synchronization gives rise to a two-point correlation functions in the full quantum problem. So there are some models where there is some connection, but in general, I would say it's not so super clear. Then it actually makes more sense to go on this phase-based representation part of quantum physics to look for kind of trajectory level effects for the expert. Okay, good, but these are this is the general fundamental idea. If you understood this, then it's already the most important part. Okay, I just, as a note again, here I don't do it because I want to save some time, but if you just take classical spins, also for these two spin terms in classical physics, you again get exactly the same equations of motion. So there's no difference in the mean field equations for the Bloch vector components compared to the classical equations. The quantumness only comes really from the fact that my single spin can be in a superposition, and if I measure it, I can randomly collapse it. That's the quantum effect here. But otherwise, the equations are really exactly the same. Good. Just some little remarks. Yeah, this is just to give you a warning, because there are so many funny factors of 2 that can go wrong. The one factor of 2 is already in this type of definition of the Hamiltonian with the I larger than j. Then there's another factor of 2, because if you really look at spins classically, you actually spin 1/2, so actually the spin components are 1/2 of the things that are derived here. And then you have 2 of those spins, so you have a factor of 4, and so it can get really funny. But I hope I got everything correct here. I just tried to stay with these Pauli matrices in general. Okay, good. This was it. It was just the derivation of the general equations. So just to show you again that it gets much simpler for the model that we will really look at in the tutorial part. So these are the full equations where I now have, you see you have the external field and you have the mean field in one point. So you see again, it's always really correlated. With the same sign, you have an external field that leads to the precession. And with the same sign, you also have the mean field of the other spins. And these are all of the terms coming from all of the XX, YY, or ZZ type interactions. So for the transverse easing model that we started to like so much, things become much more simple, because then XX and YY is 0. I don't have XX couplings or YY couplings. I also don't have an external y or z field. I only have the x field. And then I have this coupling matrix, which was my Jij matrix, which was just really j divided by I minus j as a function of the distance. So to bring it back to our to more simplified notation, this is the transverse Ising mean field equations, where I only have the ZZ mean fields acting now on the x and the y component. So the Ising part of the interactions really gives rise to precession in the xy plane of my spin. But then I have this x field, which gives rise to a precession in the yz field. But of course, the precession in the xy field is going to be dependent on the moment of time. So this is the nonlinear part. All right, so great. So now we derived these equations of motion. What's really fantastic about this, because we reduced now our set of the gigantic state vector of 2 to the n complex amplitude, we reduced it to something like only 3 n-coupled equations. Here I wanted to ask like a question to see if you paid attention. So do you have an idea to maybe even compress it a little bit further? I mean, it's already only linearly increasing, so I don't need much memory, but one could make it even a bit better. Does anybody have an idea? Related to what Raoul was explaining with Bloch vectors? Don't be shy. It's possible with 2n equations. No, you need them? Sorry? Yes, the norm is preserved because this is always...
So the equation can be written as population difference and one covariance. The complex one
goes the correct direction. Yeah, or what I wanted to get to is, it's the right thing, but then you just use the two angles, right? Yeah. You have theta and phi, and that's enough to parameterize your Bloch vector. Then instead of 3n equations, you would actually have 2n equations. But there's actually a reason why I don't like those, because if you do that, then you will get trigonometric functions on the right-hand side. Right, so then you have to evaluate tangents and sine functions and things like this, and this is actually computationally not so efficient. So it's better to spend a bit more memory here and to stay in these 3 real numbers.
The V part, do we have any special criteria about the distance to have this approximation, mean-field approximation?
This we will see later. So what I want to, I mean, this is the coupling matrix that we always looked at with this power law decay. And later we will analyze when this approximation is a good approximation. And it will depend on this power law. Spoiler alert.
I have one question that you are looking at single observables like sigma x, sigma
Yes.
y, sigma y. But for many spins, we can have many observables. Like in one spin, I can measure sigma x, the other spin, I can measure sigma y.
Yes,
So,
it's down there.
no, but they will evolve, right?
Yes, this is the thing. This is the comment here. So just look at this thing here. So of course we now have only very few equations, but we paid a pretty high price. First of all, right, we made the strong approximation, and this means if I now look at something like this connected correlation function, this is what you want. I mean, this is what we looked at last time. Right, a connected correlation function, meaning I take this correlation function and I subtract what's sort of a classical part of it. And now if I look at this observable where we saw this interesting spreading of these correlations last time, now just by definition, this observable is now going to be 0.
No, but in one spin I can measure x, the other spin I can measure
Sure,
y.
it's going to be x times y, and it's going to give you some correlation, but it's a classical correlation. And if you look at the connected correlation functions, meaning that you subtract the trivial part, it's always going to be 0. Right? So you do get some correlations between spins in the same way you get correlations between classical spins. But this is really just, for example, sigma x times sigma y. You could do that, you can compute that. But if you subtract sort of this trivial part, not trivial, it's really not highly non-trivial already, but if you subtract this classical part, you will always get 0 in this approximation. It's because you cannot have entanglement in this approximation, but you still can have classical spin correlations between arbitrary components. So it's a strong approximation, so I expect that this is not going to work all of the times. And the second big problem, of course, is now that our equations have become nonlinear, right? So really the right-hand side now depends on the components on the left-hand side. Okay, so we need a solution numerically to also integrate those type of equations because we don't have a Hamiltonian now, but we have kind of a Hamiltonian that depends now on time, right? So now, of course, we could diagonalize this at each point in time, but there's much better ways of doing this. And now I want to switch in the second part a little bit to a numerical technique that's very easy to implement and that will help you to integrate this type of equations of motion so that we can then do some fun stuff and then compare sort of the full classical spin model with this mean field spin model. Great. So Runge-Kutta method, something invented by these two very friendly-looking people. So fundamentally, what we want to solve is something really a general class of ordinary differential equations. Ordinary differential equations just means that I have equation that looks like this. I have my first time derivative of what I call a state vector. Remember, originally I called a state vector really anything, just any vector of numbers that describes the state of your system. And then on the right-hand side, I have some function that can depend on time explicitly. Here, it still does not depend on time explicitly. I still neglect situations where my Hamiltonian really changes in time. But then this function can also depend on the state vector itself at this certain time. So, of course, what I will do with any type of numerical scheme, because everything is discrete on a computer, so we're going to discretize the time. So we have time 0, time 1, time 2, and we have different state vectors all of these times. Here, the notation I use is state vector with this sub-index n, just means the vector at this particular time. And the goal is really that I have my state at times tn, and the goal is to find the one at n+1. Okay. And this is called an ordinary differential equation. And it really, it includes, for example, the Schrödinger equation, right? In the Schrödinger equation, just everything is linear because the right-hand side function that I have here is just a Hamiltonian to apply to a state vector. So this is really just a matrix multiplied with a vector on the right-hand side, right? So then this is here, we could use all of this Krylov space stuff. But now here in our mean field equations, we have a state vector that's going to look like this, right? We have the components of all of our spins in the system. I'm going to order them like that, but you can order them however you want. So I say the first I store all of the x components of my n spins, then I store all of the y components of the n spins, and then I store all of the z components. And now I could still write this as a matrix multiplication with a state vector, but now this matrix is the right-hand side, and I have to construct it at each time from the current state vector that I have, right? So now this is really nonlinear. Okay, so how can one solve this? So one may have the first, very easiest idea. Well, let's just do like a Taylor expansion of this equation. Right, so if I do a Taylor expansion, then I write my state vector at times tn plus h. Yeah, sorry, I forgot to mention here, maybe this may be confusing because these slides, they come from a different lecture series. And in this numerical literature, people usually call the time step h, which is a bit inconvenient for quantum mechanics. But okay, so for these slides, this is the time step. So this is the time difference between two different times. So, okay, so let's Taylor expand this equation. So I have my state vector at times tn plus an infinite, very small time afterwards is the one at times tn plus the time step, the first derivative of this, then plus the time step to the power of 2 divided by 2, the second derivative, and so on and so forth. And here one may have the easiest idea of all and just say like, okay, this is time step squared, this is time step h. If I make my time step just small enough, then I can forget about this term. So a very simple prescription to integrate the equation would be that I say the vector at tn plus h is just the one at tn plus h times the function on the right-hand side. Right, so and this is a scheme that's called the explicit Euler method. And it's really not a good idea to use it. You will see in a second why. Okay, and on the one hand, because the big problem with this method is that the error is relatively large, right? So the error is h squared. So you have to make your time step really small. But the bigger problem is that this is not a stable way of integrating this function. Right? You can see this in this kind of, if I do a visualization of what I'm doing here, I'm saying I have my state vector at times tn, and with this equation, what I do is I take the slope of this of this evolution here at this time, and then I just project it to the future at n+1. But if I have something now that evolves like in this direction, as I have sketched it here in this curve, then if I make an error, I underestimate the thing in this time step, then in the next time step, I will again underestimate what I have, and I will again underestimate. So what happens here is that can be very catastrophic, is that you don't have stable solutions because you kind of deviate always with your errors in the same direction. And this is not a good idea. To show that it's not a good idea, I want to just, now for fun, so here I'm just showing examples for the simplest possible model that we can think about. I want to go back to what Raoul has been introducing, just simple Rabi oscillations. Just to test this numerical idea and to see how to make it better. So let's for a second now take again just Hamiltonian dynamics, where I have just an Hamiltonian, which is just a Rabi oscillation. So I have two states. Think about it, ground state, excited state. Let's say I drive this with some laser. And then what I get is I get these oscillations between ground state and excited state, where here in between I had this pi/2 pulse, right? I have this coherent superposition, and I go up and I go down. And this would be just described by the Hamiltonian like this. Initially, I start in the ground state. And then, of course, this is trivially to solve, because we know the exact solution you can easily calculate of the excited state will just be the sine squared of t omega. Right, so this, you can go back to Raoul's lecture. This is very easy to calculate. Okay, so what I want to do is I want to just check this first order Euler method, explicit Euler method, how well it's doing compared to this exact solution. Right, and this is all the code that you could use to do that. So we will go back to writing code in the next part, but here it's just define a little time step, define like a bunch of steps. I start initially in the state 1, 0, so my state vector is really now a quantum state vector. And then I want to just compute the populations. Right, so these are just all the populations of the excited state that I compute, and I just now integrate this over times with this first order Runge-Kutta method, which I defined here. Right, so here is just how you typically would implement this type of Runge-Kutta things. So the starting point is always to write a function that implements the right-hand side of your equation. Right, so everything, which is this ftn_yn, you have to write a function that really on a computer does this right-hand side. Because if you have this, then everything is simple. So here, for example, for my Hamiltonian problem, which is again linear, then my first order Euler step, sort of this function would just be here in this bracket here. It's just the Hamiltonian applied to the state vector with the imaginary unit. And then the Euler step would just be just doing this thing here, right? Okay, that would be the function that does one time step with this Runge-Kutta 1, and the function on the right-hand side is f of t, is what's in the parentheses really here. Okay, so let's see what we get if we do this. So if I do this evolution, it's exactly as I had predicted. It's this time step 0.05 that I used before. Right, it was here, time step 0.05. You see that the problem is that the real Rabi oscillations would be just the black line here, but this numerical, this silly numerical solution that I get is the yellow points here, and you see that these oscillations get larger and larger and larger. I get completely unphysical results. The population in the excited state becomes larger than 1. It cannot really be. And this is just really a consequence of this Euler method. Right? You can also see directly from the quantum equations, if you would do this Euler step, it would look something like this. So at n+1, you get a state vector that looks like this. Now, if you compute the norm of this state vector, you always add something that increases. And that's the problem that you see here. Your states become unnormalized, and catastrophe happens. So bottom line is like never, ever use this idea. Instead, what's much better already is to use what's called a second order method. And here I just introduce what's called the midpoint rule. And this is now quite obvious. It's obvious in the sense that if I do this Taylor expansion, right, it would be much better if I expand my time step with the slope not at the beginning of this time interval, but instead with the slope in the middle of the time interval. Right, so ideally what I could do, for example, here in particular this midpoint rule, would be that the slope that I use at the middle of the time step is actually 1/2 the state vector at times n plus state vector times n plus 1. Right, so I take these two state vectors, I take 1/2 of it, and then I evaluate f. Right, f always gives you the slope, right? Because it's the derivative is the function f. So then I evaluate now the slope kind of as an average of these two points. And that's called the midpoint rule. And if you do the math, and if you check, for example, the error of this method, which can always be done by Taylor expansion, it can get quite messy, I warn you. For the second order method, it's still kind of okay. But for higher orders, it gets more messy. But then one can see that the error that one now makes is actually of order h to the power 3. Okay, and this is called the implicit midpoint method. And of course, at this point, when you look at this, you say like, yeah, but this is a bit stupid. Right? Because in order to implement this method, I actually do need to know my state vector at the time tn plus 1 already. Right? That's what this is called an implicit method. In the numerics literature, implicit means that the right-hand side of your equation already depends on state vectors that you actually don't know. Right? So then you may ask, how on earth can I implement this? Well, the trick is just to use iterations. The trick is really that I have now the method, I write it down like this, and here I have the yn plus 1 on the right-hand side. But what I can do is I can just do an iteration and reinsert this yn plus 1 on this right-hand side. And then what I essentially get is I get sort of a two-step method. So you can get first an approximation of the state yn plus 1. And you will see what you get is simply an approximation of this using the Euler method. Then one can, from this, compute this slope, which I call k1 here. So this is really the first step here to compute this k1. And then with this k1, I use it in the second step to get the approximation for the real yn plus 1. And if one does it that way, one sees that the error is still of the order h to the power 3. Okay, I mean, there's a lot of math that I'm kind of skipping over here, but I really want you to understand more the concept behind this. And actually, from an intuitive point of view, it's actually quite clear, because what you see now in this method here is that you kind of first use a step to get a rough estimate for a slope, and then in a second step, you improve it here by computing the slope with this vector that you computed here before. And this gives you an error which is power time step to the 3, and it's a second order method. And you see it's called second order method because now if I do this, I need actually two function evaluations. Right? So the numerical cost that I will always have is evaluating this function that's on the right-hand side. In this Euler method, I just used it once and I only got an order h squared. Here I use two function evaluations and then now I get an error which is actually h to the power 3. Okay, and now if you do this, so the modification of the code would be just something like this. Here you can literally write this code. First, I produce the k1 from my state vector y with the time step, with half the time step here, with one function evaluation, and then I use the second one here written there, and I get the second one. And if I do this, then I now see that my numerical simulation is going to give a stable solution. To be a bit more quantitative, I can compute the error of the numerical solution compared to the exact solution. And I see that the Euler method just gives errors that are always positive here, and they get larger and larger. Whereas here I also introduce the errors, but now the errors are much smaller already because they are h to the power of 3. Right? This is still the same time step that I've been using. And on top of this, sometimes the error is positive, sometimes it's negative, sometimes positive, negative. And that's why this method is now a numerically stable method to simulate things. All right, so now just to show you the Swiss Army knife thing, so what is usually the best method to do is sort of the so-called fourth order Runge-Kutta method. There are actually multiple fourth order methods that one can write down. Here, I'm not going to derive this, because to derive that the error in this method is h to the power 5 is really a mess. You have to do Taylor expansions to very long things, so I don't encourage you to do that, really. But one can derive this method, and it works sort of in 4 different steps here. It's just really combining different estimations for the slopes. So here, first one uses the slope here to estimate the point here. Then one uses this to estimate the slope here. Then from there, one goes to a better estimation, and then one has this other estimation of the slope here, and then one adds them all up in a particular symmetric way. And then one can do this proof that the error is really going to be h to the power of 5, but I'm not going to do this, but it's really, really messy. And this is a method which is very popular, I would say, and there's a simple reason for that. It's just because h to the power of 5 gives you a really, really small error. And so typically, what one typically wants in practice, if you want to get smooth plots of something, you typically want to have like 100 data points, right? So, and then typically in these dynamics, like to the spin models, right? We have the dynamical timescale is the spin flip-flop. You typically want to go to a timescale of sort of 10 or so. So that means you really want to use, typically, if you normalize the units properly, you want to use time steps which are something like 0.1. And if you use 0.1 time steps, then 0.1 to the power of 3 is just 10 to the minus 3. It's not so small. So second order is not ideal, but if you use a fifth order, this fourth order method, you get really tiny time step errors, which are usually more than enough. So this is kind of always a sweet spot where you only evolve your state to the points where you want to plot them. Otherwise, you have to do intermediate points and then plot them again in intermediate points. Otherwise, you get too many data points anyway. So that's really a general method I recommend. It's very easy to implement. We will use this method explicitly now in the next part when I just show you how to write this mean field code. Here's just the example how you would do it for this trivial example. Again, I just really literally can translate this code. So this is the function. I have now 4 function evaluations because the error is to the power 5. And I compute just these vectors k1, k2, k3, k4. So all of these are really vectors. All of these are intermediate state vectors. And then I just add them up in this particular way and return it. And if I use this function, I see that I get also a stable method here. The errors change the sign, and the errors are really small. They're now 10 to the minus 7. Right, so now I can check. This is always good to do. Whenever one writes some function like this, it's quite easy to make mistakes. So, and I had all this nice theory telling you how the error should scale, but it's always good to just check it. So here, what I do in this plot, I take the exact value at some particular time. I took this time 3 pi over 2. And then I plot the error that I get at this particular time from the exact solution. And I plot this error as a function of the time scale. So the time step. So h smaller makes the time step smaller, smaller, smaller. And here I get the numerical error for smaller time step going down. This is a log-log scale, which means that these black lines here, they are power laws. And you see now for the first order method, the error goes at h to the power 1. For the second order, it goes h to the power 3. And for the fourth, it goes h to the power 5. All the way to 0, where again, you see what's happening here, these little wiggles. It's the machine precision kicking in again, 10 to the minus 16. At that point, you're more than happy. Okay, and it's just funny to see here, of course, that this explicit Euler method, right, it is h to the power 2. Also, the error should be h squared. So why not h to the power 2? Well, because I showed you before, it's not stable, right? So now I'm at a fixed time, and now all the errors keep adding up. So actually, effectively, the error goes just linear in the time step, right? Because in order to win with this method, you really have to make it so tiny that even if you add like up tens of thousands of these steps, they should still not give you a significant contribution because they always add up in the same direction. That's what in practice means to have an unstable numerical technique. Okay, good. So far, so clear. If not, you can just use this prescription as a formula to implement this method. All right, so great. So let's go to, again, the practical part. So the goal is now, I want to now implement this. and I want to really check with the exact solution when is this mean field approximation good for our transverse easing model. So I'm now going to use this fourth order Runge-Kutta method in order to solve the mean field equations for our spin model. Hands on. Do you have any other question so far? Is anything unclear? Okay. Great. Actually, I wanted, okay, first a few preliminaries before we actually start really going. So again, I want to just introduce the strategy of how I want to go ahead. So as I mentioned, it's always, the initial point is always to write a function that implements the right-hand side of my ordinary differential equation. That's always the initial part. So I want to write a function that really, for our transverse easing model, if I write on the mean field equations, then the right-hand side is this. So I have to write a function that really evaluates the right-hand side, which gives me this high-dimensional slope of my big state vector at that time. Right, so the first thing what we're going to do is we're going to sort of design a state vector. Well, I already showed how to do this. And then I want to construct really the function that implements this right-hand side of the equation. So really this function here. Just then, looking ahead, the second point, then we're going to write this function that does a time step using this Runge-Kutta 4 method. And then finally, we'll just want to compute and plot some observable dynamics and do some actual physics. So for designing the state vector, I already essentially said before how I wanted to do this. The way I wanted to do is I want to write all of the x components as the first n elements of my state vector. Then I use the y components and I use the z components. You will see in the code why doing it that way can be quite efficient. Gesundheit. And then I have the initial state is the one where I start with like the spins down, for example. Right, this would be the spin down state. This is the initial state I want to look at today. The initial state is all the spins down, which in the state vector now just means I have 0, 0, 0, 0, 0, and then I have -1, -1, -1, -1, -1. Right? My Bloch vectors are all pointing down. So initially, all the z components of a mean field description are going to be -1 initially. Okay. Good. So let's get to that. So what I did here is, again, the same way that I did everything before. So let me start again. Julia. So I made now really a new script, which I call easing mean field. I know my notations are always changing, and that kind of pretty bad. I have all of the same packages we used the last time, and I actually left all of this exact diagonalization things that we did last time. I left it in there. Right. So this is just the functions that is this sparse evolution using this Kirillov space. I have it there because, of course, I want to benchmark afterwards my mean field solution with this sparse, with this exact solution. Okay, so as I said, we want to do a function that does really the right-hand side of our equation. So let's start writing this function, which is, how did I call it? Let's call it transverse easing. And so what do I have to give this function? Well, it depends on the state vector, right? This is nonlinearity. So my state vector, let's call it capital Y. Then what I'm going to need is I'm going to need this coupling matrix between the spins. Right? Let's call it Vij in this case. Then again, I have my field in the x direction. And to make things a bit more efficient, let's give it the number of spins that I have, capital N. Okay, so right, I said before that I want to design my state vector with first the x, the y, and the z component. But of course, this is just a design that I have in my head and that I have to stick to. But to define this, what I want to do is I want to define a range, right? So for example, the range of the x elements in my big state vector going to be 1 to n. This is the first n element that's going to give me the 1 to n, so the x component. So these are the indices that give me the x elements of each of the spins. Right, so this is really a range. Right, if I do something like 1 to n, this is first command, first mistake. Right, if I do something like this is a range 1 to 10. This is just telling that this is an index range. I can turn this into a vector, for example, this way, and then I get 1 to 10. So these are all the indices that give me the x component of my spin. Then I want to keep going with the y components, where I start them from n plus 1. I go to 2n. Right, and finally, the z component of my state vector I defined now as 2 times n plus 1, going all the way to 3 times n. Okay, so this is just for me, so that I define these components. Where's the x components? Where's the y components? Where is the z components? Okay, then what I want to get, I want to return the slope. Right, so in these plots for Runge-Kutta, I was just drawing it, one-dimensional for a one-dimensional state vector. But of course, the slope, this is of course a high-dimensional object. Right, so what I want to return is really a state vector. Let's call it dy. And again, there I can use really, again, quite easy notation. I use again this similar keyword, which is the same. So if I do this, then this just creates a vector which is identical to this one in terms of the data type and also in terms of the length. Right, so if I make a random vector, let's say I have a vector with 5 elements, let's call it A. Right, if I do similar B, what am I doing? Similar A I wanted to do. Right, so now I create a vector which has also 5 elements. It has the same float 64-bit floating point number. Now you just see what's written here. It has some random crap in it. Because, right, so what this similar does, it just allocates this vector on your memory, but there can be some random bit strings lying there, so whatever you get here is something. It's very different from if you do like zeros, right? So zeros, 5, this really creates an element, and then it initializes all the elements with 0. Okay, but here I'm going to fill all the elements of the y, so I don't need to initialize that. So that's one way of doing it. Okay, so now let me just for a second go back to the equations that we want to implement. So here I want to put your attention to something like here. So I see this, all of this thing here, right? It's going to give me the mean field, meaning it's give me one number that is a field that leads to the precession. But then if you look at this equation here, right, I sum over j with this vmj, and then I multiply it with the zj component. Right, so if you look at this, this is a matrix vector multiplication. Right, you see this? So this is really, what I can do here is I can really just say, I take my coupling matrix, which I call here Vij. This is a matrix, an n by n matrix. And I multiply this matrix now to my set components that are in this range here. Right, so this is going to perform the sum. And then this is give me m different numbers. For the element m, this gives a number. For the m1, this gives a number. For m2, this gives a number, and so on. So the vector that comes out from this matrix vector multiplication, it's just going to be a vector of all of the mean fields that I have. Right, so this is the reason I wanted to keep these components of the spin together, because now I can use a matrix multiplication function, which is something that works very efficiently on the computer. Good, so let's call this the mean fields with plural, because this is an n-dimensional vector which gives me the mean fields in the z direction coming from this Ising term. Okay, and now I'm going to use this field together with the field hx to update my state vector, right? So now I have to go here and I have this field I computed once, it's the same field here, and now I have to just do these precession terms. So what I want to do now, I want to fill my my dy state vector. So first let's start with the x components. Right, so the x component was minus mean fields, right? So now do I do a pointwise multiplication with the z components. Right, so this is implementing this term here, the first term. I have the mean fields in the z component. I multiply it with the y components, and it gives me the x components. right? So the new x range of this derivative vector is going to be minus, wait, was there minus? Yes, there was a minus. The mean fields times this set range. You see it? Okay, and I keep going, just doing all of the other parts. So now I have the y range. The y range, right, is with the positive mean fields times the y of the x range. Right, so this is a term where here I have the x, this is the mx components. These are again the mean fields, and I update the y components with this, so this looks like that. Has an opposite sign for here, so you see this is kind of necessary, otherwise you wouldn't get any precession. And in addition, I also have the external field, right? So this is really just a number now times the set range, right? Because the field is in the x direction, so it gives the precession in the y-z plane, so it enters with a minus sign here. And finally, the z components only see the external field, which is plus hx, I think, times y ran. So if you see, you will see if you try this yourself, if you make one little mistake in the signs here, you usually recognize immediately because your equations blow up. Right? So this is a very particular form that gives rise to this precession. If you don't use this, things are going to be bad. Okay, and now I return this slope. And something I completely ignored so far is this factor of 2. Right? The factor of 2 shows up everywhere. So that there's a 2 times dy. I do it just at the end, right? If I add the 2 everywhere, then, okay, I mean, normally the compiler is smart enough to optimize these things out. But now I only have to multiply these 2's once, so technically less principal operations. So it's good practice to kind of minimize this. So I put the 2 just here at the very end. One could also just leave out this 2 and just use a different convention for the factors of the coupling matrix, but let's stay consistent here. Okay, this is the function, so let me just see. Okay, let's just use it like this for now, and then see how it then works afterwards. Well, let me just check. So now I include again this file. Okay, first time I create this function here, so let's see just fundamentally if it works. I mean, I just try, let's say I have 10 spins, right? Then let's say I have put in here a random vector with 30 random elements. I put a random n by n matrix, and then I put field 1, and then this is for 10. This should work, yes. So it gives me some vector, it just does one operation, it gives me the slope of this random vector that's coming out. I don't know if it's going to be exact, but I'm going to find out when I want to do the time evolution with this. Great, so one little thing I want to do here, a bit of advanced Julia stuff. I will explain in a second what this means. I want to put this one here. Up. Yes. Okay. Okay, why do I do this? Well, it makes it go faster. The reason why it makes it go faster is the following, because you may know, I mean, this is again advanced things. Also things like this here, like I have this right-hand side function which passes on a state vector, right? So the argument of the function is this whole state vector, but of course it would be computationally kind of silly to copy that whole state vector into the function, right? So, yes?
I think that in the equation of x, it's y and not z.
You say my equations are blowing up. In the x, you're absolutely correct. Here it should be y. Too bad, otherwise things would have blown up. Okay, so what I want to just say is, I mean, of course, if you have now the right-hand side and you don't make a copy for this vector for the function. Instead, what your computer should do is you have all the numbers that are somewhere, all the bit strings that are somewhere in the memory. And the thing that when you want to pass this vector to the function, what you want to pass, you just want to pass kind of like the memory address of that vector to that function. So Julia is doing this automatically. Like in C and C++, you can do both. You can pass it by copying, or you can pass it by this memory address. Julia passes it automatically by this memory reference. Now the same thing you see happens in expressions, something like this here. Let's just take the min field. Right? In min field, I want to just do this matrix multiplication with only a subpart of this vector. Right now, if I want to use only here this min field of the set components, and say the set components, they start here, right? In this expression, I shouldn't create a new vector, which is the vector of the set components, and then multiply it to the matrix. I should just tell my code to, right, this is where the set components start. I should just tell my program to put the starting point for this thing here, and then I don't need to copy anything. And in Julia, one can avoid this copying operations automatically in this type of range expression if one puts this add views in front. Parentheses closed, just for some advanced things. So if whenever one has expressions like this, one uses this add views, it usually makes things go faster. Okay, great. So good, so we did part one. We have now our state vector. And we have the function that implements the right-hand side, hopefully not with any more mistakes. So what we have to do in the next step now, right, we have to now go and do this Runge-Kutta step with this function. Right, so I cannot do both at the same time, or maybe I can. Let's just move this over to this desktop here. Right, so now I really want to implement this. I'm not sure you can see this, and I want to really write this function Runge-Kutta. So I want to write the function that does a single time step according to this Runge-Kutta fourth order method. So let's call it RK4, transverse easing. Again, what does this function need? It needs my state vector. It should update the state vector. It's going to need, again, the coupling matrix. It's going to need the transverse field. It's going to need the time step, which I now call dt again, and I'm also going to give it n. Okay, so now if I want to write this function, I see here I have this kind of f notation, and here previously my right-hand side equation is kind of messy, so I do something which is just really for convenience. I just write a simplified function which I just call fy. Right, I want to have just a single argument function just to make my expression looking cleaner. This is not going to cause any overhead because Julia compiles this away. And I want to just this function be the same as this transverse easing function. Y, and then I just pass on all the other arguments that I already have. And n. The time step I don't need, of course. Right, so this is just calling this function here. And I just simplify it because I want to have a single argument. Right, so now I have really exactly the same as here, and I don't have a time dependence explicitly. Right, I could also have functions like this, but luckily, still it's explicitly time independent. And now I can just write this down super easily. I'm going to do something more convenient. I'm going to define half a time step because I'm going to use half the time step all the time. And then I can do literally just copy what I have here over there. So K1 is the function of y. K2 is going to be the function of y. Y plus half the time step times K1. K3 is going to be the function of y plus half the time step times K2. And the K4 is going to be the function of y plus, I wouldn't need this pointwise, I just do it because I really like it. Pointwise K3. Right, so these are my 4 estimations of the slopes at different points in time. But this was really one full time step here. Yes, this is because here's a full time step here, the half time steps, and looks kind of okay. Okay, and then now finally I do the update. Y is y plus, and now I do dt over 6. This is really magic how this error works out, and then the time step error is small, but it's always good to check it with exact solutions as I did before to be really sure that it works. And then I do pointwise multiplication of this time step with just k1 plus 2 times k2 plus 2 times k3 plus k4, and this is rather ugly, so let's do it a bit nicer. 2k4, 2, something like this. Anyway, we'll see if I made a mistake. Oh, yeah. I have to. Okay, I think it looks okay. Oh, yeah. You're absolutely right. I just said I love this point and then I forgot it. Okay. I love this automatic bug fixing.
The last line pointwise addition.
Uh,
The last two number. K3 and K6.
mm-hmm. You mean here? I mean this one?
No.
Ah, yeah, okay. Yes, I mean, yeah.
Also the previous.
Yes, okay. By the way, it would be doing this also without the point, because the plus is anywhere by default point. But it's I like it very much. Okay, good. Enough points now. Okay, so this is in principle, unless I made some bug, which for sure I still did. In principle now, this is really fully enough to really start doing simulations. So I suggest we just do this, and then compare it to the exact solution. Right, so let's see what the, my plan was here. Let's shift this again over there. Okay, so now all that we want to do is we want to really take an initial state all down. We want to simulate the evolution with the Hamiltonian, and then again compute an observable. So here the observable that I want to look at now, last time we had the set components of all of the spins, how they evolve. Now I just want to look at the sum of all of those components, just to make the plots a bit easier. All right, so let's do it. So this is the time where, again, I'm going to write now just a main function. So this is the actual program. It's actually going to return nothing, because it's just going to do what I want to do, evolve the system and plot the system. So let's take first a small system. Let's take, because we want to compare to the exact simulation. So to not waste time, let's do 10 spins. My coupling thing was again 1. My field in the x direction was 1. And let's say we have short range interactions for now. Let's say alpha 3. Okay, just random numbers. Time steps, as I said, 0.1 is going to work. Of course, good practice, something that I'm going to skip here. It's always good to check for convergence in the time step. So always run your simulation with multiple time steps. See that the results converge, just to be sure. But here, this is, in the interest of time, I'm going to skip this and just use this time step. I can change it a bit and then see what happens. Okay, so we have a range of times. I do it a little bit different now that we have introduced these ranges properly, like this. And the number of steps that I'm going to use is just the length of this range. Okay, good. So what I want to do actually first, I want to again do the exact simulation just to see more or less what we're going to expect to see in this case. Right, so the exact simulation, I had the function with this sparse simulation here. And yeah, what I did here, I just output only all of the set components again of my spins. If you remember, this was what we used to plot really the evolution of all the individual set components of the spin. So in order to do this simulation, I can just get all of the set components. Let's call it a set ED for exact diagonalization. This comes from my sparse transverse easing simulation, where I use N, and I use, this was J, should write J, alpha, hx, dt, and steps. Okay, so this, if I now include this thing and I run my program, so if, again, first time it takes long, but now it does the evolution. This was the exact evolution we did last time. We have this is set, so let's plot now the sum over this set. So what I want to plot is really the sum over this set ED. Right, and remember in this, the way that we output this was just this matrix form. Right, I had the time in this direction. This is the first dimension in Julia, and then I had the index I of the spin in the other direction. That was the second index. So in order to make the sum without writing a loop in Julia, I can just write sum over this dimension 2. This is gonna build that sum. And I want to plot this. So just what I want to do is let's do this as a pointwise plot. So no lines. I just want to have points. This is in Julia, you call it scatter. The x-axis is the time range. This should be the sum in the dimension. Okay, and then let's give it a label. This is exact diagonalization. Okay, and this is going to be a plot. And I'm going to display this plot just to see what we get. And let me do something like this for now. I choose the transfer field to 2, and then I get something like this. Right, so this is exact evolution of the set component. Actually, to make things a little bit nicer, or let me just cheat, just to save some time. I have all of this down here. Let's just make nicer labels so that we know what we have. Right, I want to have the x label defined, which is just the time. And as the title of the plot, I'm going to say what I'm plotting, which is the sum over the set component. Okay, this is what you see that you get for the averaged fully exact quantum evolution. And it's actually quite easy to understand what this is. Right, because imagine this transverse easing model, right, I have the term, which is the, I'll write Hamiltonian again. Right, I had this J, I, J, sigma set I, sigma J set, right, so this is the interaction. And then I have the transverse field plus the Hx sum over I, sigma x I. Right, so if you just look at this last term here that you see, right, you could realize again that this last term again is a sigma x, so this is kind of again a laser drive of a two-level system, no? Right, so if I write this just as, this is sigma I plus sigma I minus, no? Right, so this is also, this Hx, I can think about it as a Rabi frequency driving my two-level system. Right, so all of the two-level systems, they get driven by this Rabi frequency, but now you have this interaction with the other spins. Right, so and what does this interaction with the other spins do? I mentioned this last time, but if you take out this observable, which is a single spin observable, it's the evolution of one of these spins in the middle of a bunch of other spins. Right, so you can think about the other spins as being the bath for my spin. Right, so what I get here is really Rabi oscillations which are going to be damped. Right, so if I do proper optical Bloch equations, I will find actually quite a similar evolution to this, Rabi oscillations and then damping. Right, so if I make the field a bit larger, if I say this is, let's put it to 4, then I would drive it stronger, and then I get faster oscillations. Right, so this is just to prepare you a little bit about the physics that I want to look at here. Okay. Okay. Great, so this is just what the exact solution would do. So now let's see what, if you do the mean field with this Hungekutta, let's see what this would do. So let me just comment out this plot again. So these are comments, so this is not going to do it. So let's do the mean field solution. What have been missing so far is I have to define the coupling matrix, which I did not do before. This is something that my function needs, Vij. Sometimes I call it Jij, Vij, so let's call it Jij here, so I make less mistakes. Right, so here I can say, okay, this is again a matrix. Here I use again a different notation. I always use a little bit different notations, by the way, not only because I'm a messy person with this, but also just to show you different ways of doing it. Again, what we want to do is we're going to fill this matrix fully anyway. So it would be, I could use just, this function that I chose, it's like zeros n by n, but I want to just allocate it to save some time and not initialize it. Right? So I can also write things like undef n times n, and now this is an n times n matrix, which is just randomly whatever was in the memory there. Okay, so now let's fill this matrix. So I want to sum from 1 to n. And so here in this outer loop, I can already set, this is just exactly the same as we did last time. I can already set my diagonal elements to be 0. Right now, of course, I have to set the diagonal elements to be 0 here because here I didn't associate them at all. And then in the other loop, which now I actually let run over, again, just half of the indices, just to not waste things. So I just make a second loop from I plus 1 all the way to n. And here now I can set this matrix, so II, Jj would be just j divided by Jj minus II to the power alpha. Right, no need for an absolute value here because Jj is always going to be larger than, it's always going to be larger than I. And then, of course, I have to set the other part of the matrix too. So I have to also set Jj and II to be the same. Right, so I don't have to recalculate this. I just also copy it over. Okay, good. This is the coupling matrix. Let's hope that it works. Actually, let's check that it works. Let me return this from my main function here. Yeah, so this is the coupling matrix. Makes sense. I had alpha 3, so the off-diagonal, the nearest neighbor coupling is 1. This is j, then it's 1 over 8, and so on. So now everything's going to be actually quite simple. What I'm still missing is my state vector. Right, so I define my initial state vector. Remember, I wanted to have it -1 here for all of the set components. So let's define it like this. Like zeros, 2 times n. So this is going to be a vector of 2 n zeros. And I'm going to do a minus 1s n. Right, debugging. Let's check if we get the right thing. So this is the state vector that comes out from this. Good. Just do the time loop for the way I'm doing it equals 1 to the number of steps that I had. Okay. I have one last thing. I want to get my values for the set components. This is my observable that I want to look at. This again is a matrix, which is again just float 64. Of course, it costs more time to write efficient code compared to just write zeros. And I want to do this again, a matrix where the first dimension is the number of steps. Remember, this is the time dimension. And the second dimension of this is just going to be n again. So what I do in my time loop, now I first evaluate the function, but for evaluation, I do have nothing to do actually, right? So I just have to do ftt tuck. Did I forget something? Please correct me if I get something wrong. And I just associate pointwise all the set components in my state vector, which here was from 2 times n plus 1 all the way to the end of the state vector. Right, so this is just writing at that point in time from my state vector the set components into this matrix for that time. So this is evaluating my things. And then here comes the update, which is just our update function with y. Then we give the hx, time step, and n, I think. Okay, well, let's return y. Let's see what happens. Good, it gives me something. It gives me some state vector, which is now the one at the end of the time. So let's see if we get something similar. So again, I don't want to really return anything here, but instead I want to make this plot comparing the exact solution with this mean field one. Right, so now on top of this, what I really want to do, I also want to plot the mean field result. In Julia, I can add to this plot just by using this exclamation mark. This is just adding something to the plot that's currently open. Again, for my time range, this is to define the x-axis, and I do again the sum, as said, now only with the mean field solution, which I get here, and summed over the second dimension, and I label it mean field. Okay, I think this is all that I want to do. Let's see what happens. And you see what you get here. Right, so it's quite clear what's going on. Again, so the mean field solution is now the, oh, that's the wrong one. The mean field solution is this line here, the orange line, whereas the exact solution was this blue point. Right, so the mean field solution here keeps just oscillating. The reason why it keeps oscillating is now because this was for a strong field. This hx was larger than this j. Right, so then really all that happens is this field is dominating and it's classical spins that keep just rotating. And the reason why I don't see the damping is because now I don't have entanglement with the other spins, so I don't have entropy with the other spins, so I don't start to entangle things. So because all of my state vector that I have, it's going to stay pure, right? So I cannot get this effective thermal behavior. And that's the problem that I get. Now, of course, let's see where this works. So I'm almost done anyway. So one limit where this works, let's make this field now smaller and see what happens. This is already, you see, you don't go actually anymore to really, right, in the exact solution before we were fully thermalizing to a value of average 0 spin. Now we already have much smaller spins here. We actually get more interesting behavior in this low excitation regime now. But it still mean field only works for the relatively short times. But now if I go to a limit where I make this mean field really small, so now I go to an approximation where I start with all spins down and then I just go to a low excitation regime. So let's say 0, 1. Right, and now I see that the mean field becomes really, really good. Right, so this low excitation limit is really something where this mean field can give you kind of an excellent approximation. This is now just because these quantum correlations for high excitations, they don't play an important role. And then you get really this, also in the quantum model, for low excitations, you get the same type of dynamics as you get from classical spin models, essentially. All right, and this is what I wanted to really show here. So here I have also these plots summarized. I'm amazed it worked the first time I was coding it. I was really expecting. Well, I would have had a bug if Elaine didn't warn me. Okay, so really one thing, this is another example. Now, okay, it works for, I want to ask you the question. So it works for this low excitation regime. Another limit where it actually works very well is if I make my interaction exponent smaller, if I make my interactions more long range. Right, so this is an example where I drive, again, with relatively strong, but I also have these long range couplings, and mean field works very, very well. And this is what you see really here, what also deriving mean fields in other ways. Sometimes you hear that when you have a very large connectivity, then mean field becomes much better. And it just means if you have one spin and you have many of the other spins talking to that spin, then these mean fields, they average out more efficiently, and then the classical model becomes better. Here, if I make the interactions more longer range, then more spins talk to each other. And then also mean field becomes better, again, in this limit. that's what I wanted to show. So now I recommend, if you do this, playing a little bit with this transverse field and check when this mean field is a good approximation and when not. Okay, actually I have, how much time do I have left? Yeah, I will shift this to the next time what I wanted to show. I wanted to now show also some simulation I did from the Gross-Petersky equation using this Runge-Kutta thing. I will shift it to next time because what I want to do is, let me just skip over that. There are nice videos here, which I will not show, but it's going to be fun next time. So this is just a recap of what I did today. So we started really to look at now approximations where we go beyond this exact full state vector representation. So quantum mechanics is always this linear problem on this gigantic Hilbert space. And what we did today is we reduced the Hilbert space. We can now treat much larger systems because our state vector is very small, but our equations became non-linear. This is a typical feature of this mean field approximation. Same is true for the Gross-Petersky equations that I will show some mean field simulations the next time. Then the second part, I had to introduce this Runge-Kutta method, which is really a series of methods to really do this ordinary differential equation evolution. In particular, this fourth order method, it works pretty well. And then I use this fourth order method to do the mean field simulation for the spin model, where I have derived these equations of motion before. And we saw that there are really some limits, low excitation or high connectivity, where this mean field can give kind of excellent approximations. So, and then the next time, really the goal for the next time is now to go beyond these product states and to introduce something like matrix product states, which is a very cool technique. Unfortunately, this is really would be a lecture series by itself. So I will not do any tutorial style there. I will really just introduce the main concept and show you some code examples so that you can get started using these methods if you like to. Okay, that's it. Have a nice evening.